Hello, I'm Philip Zucker. I'm very excited to be here today talking about Knuckledragger, a low barrier proof assistant I've been building. You may notice that this is in a Jupyter notebook. You can run it yourself by going to this link. One of the cool things about being in a popular language like Python is all the infrastructure that comes along with it. And this is an example of that. So I can install this using pip. I can install Knuckledragger, which is available on GitHub. Okay, so what am I going to be talking about today? First off, Z3 is awesome. The Z3 SMT solver is super powerful, very popular. It's kind of a name brand in terms of automated theorem improvers. And it can solve a lot of problems on its own. But it's not perfect, right? There are various reasons. Really, the problems you can express to Z3 are so difficult that you have no reason to expect any system can just do it on its own. And that's where enters Knuckledragger. It's a systematic and rigorous way to sort of guide Z3 through problems in a way that it couldn't do just on its own. I'll show a short demo of Knuckledragger, and then we'll discuss the kernel, the core idea of Knuckledragger, of like what makes it tick. And then finally I'll have a feature smorgasbord of just all sorts of things in this library. I've been trying to make this a usable proof assistant. And you know, there's the core idea of a proof assistant, but then there's a lot of stuff that has to come in around it to actually make it more usable and fun. Okay, so motivation. Z3 is an awesome SMT solver, and its Python bindings are great. So a example of how you might use Z3 is you can talk about a property of bit vectors. So here I'm making a bit vector, 64-bit bit vector. I want to say that I'm going to prove the theorem that the bitwise OR of two bit vectors is equal to the bit vector itself. Okay, and Z3 comes back immediately and says prove. Now what is Z3 doing? Z3 is negating this statement and seeking a satisfying instance of the negation of that statement. It is seeking a counterexample. And if Z3 can exhaustively show that there are no counterexamples, then the statement is said to be proved. Okay, so that's great. Also, Z3 has support for all sorts of sorts. It has a built-in notion of integers, real numbers, sequences, some other things. But one of its subsystems is a algebraic data types, which you might find in OCaml or Haskell. So here I'm defining a piano natural numbers, which is a zero constructor and a successor constructor. And I can define an add function that operates by pattern matching over the first variable. Seeing if the first variable is 0, then I return the second argument. Otherwise, I recurse on the predecessor of the first argument. And I can then ask a property of this addition function. If I add 0 to n, is it equal to n? And Z3 can indeed do that on its own. Given the definition, it can prove that property. But Z3 can't do everything. Really, once you start trying to express interesting properties, you tend to bring in quantifiers, the for all and exist quantifiers. And Z3 is dicey. Its behavior, sometimes it succeeds very well and very quickly, but sometimes it just goes off into the stratosphere or just would never find the appropriate instantiation. And what do you do at that point, right? Another thing Z3 can't really do is it has no built-in notion of induction, which is necessary for some things you want to ask or prove. So here is a very similar looking property. If you add n plus 0 is equal to n. And because of the asymmetry of how I define my addition function, this one requires an induction in order to prove. It doesn't follow by super simple reasoning from the definition. And if I try and run Z3 over this, it does time out eventually. It would never come back, and it can't prove this property in one shot. Okay, so here enters Knuckledragger. Knuckledragger is an interactive theorem prover designed as a library in Python. So it's not trying to reinvent the world. It didn't make a new concrete syntax. And the metaprogramming language of this whole thing is regular Python, a super powerful and very popular language. The whole thing is as shallowly based around Z3Py, as shallow as possible. Again, trying to be unopinionated, trying to be a very shallow layout and use what has already been made and already well designed. And the main thing it kind of brings to the table is a notion of proof object versus just formulas. So a a proof, a property of a thing that is proven is the formula it's a proof about. But a proof is not the same thing as a formula by any means. Okay, so what does this look like? Instead of importing Z3, I import Knuckledragger, Kdrag, and the SMT module, which is literally a re-exporting of Z3. The term data structures and formula data structures of Knuckledragger are literally the Z3 Pi data structures. There's no impedance mismatch here. And I can ask basically the same question. To prove the bitwise OR of a bit vector is equal to itself. And now you notice it's the same looking function, except now it's kd.prove instead of z3.prove. And it returns something instead of returning nothing. And what it proves is a Knuckledragger proof object. And you can see that because it has this turnstile here, which shows that it is a proof object. It is a proven formula rather than just some arbitrary formula. And the type of it is indeed not a Z3 thing. It's a kdrag.kernel.proof. And inside of it, it does have this Z3 object. So this is a Z3.quantifier ref. Okay, so anything you could do before through Z3.proof, you can get it to go through. Great. But also, the thing is now to attack those problems that I said Z3 couldn't do on its own before. So Knuckledragger supports algebraic data types and, importantly, induction over those algebraic data types. So I can define an inductive through the system. This is making the same Z3 data type as before, but it's registering an induction principle inside of the system. And I can also define an addition function, the same as I did before, except now I'm defining it. This is registering a definition inside of Knuckledragger. And also, I am using the helper function kd.cond, which I think makes the definition look a little bit nicer. That is a definition by cases. In addition, I can register into Knuckledragger. It has an operator overloading facility, such that whenever you use the Python operator plus, and it's over nat objects, things of Z3 sort nat, now it will use this add function. I'm registering it here. It's very similar to Python's single dispatch is how it works. Okay, so I can run that and define this. And then again, things that Z3 can do in one shot, I can do as the same as before. But now, I need to add by, with this by keyword, lemmas that might be necessary. And Knuckledragger checks that these lemmas are proof objects and not arbitrary Z3 formulas when it goes through them. So again, we can run this, and it is indeed add suck y, x. We can see that it is returning a proof object from these things. Okay, but now we also want to do a really interactive proof. Okay, and for that, Knuckledragger offers the kd.lemma objects. So again, this is not any different than, this is ordinary Python syntax. It's all embedded inside of ordinary Python. You define a goal of a thing that you want to prove. This is the analog, if you've seen in Rock or Lean or Isabelle, their proof modes. This is doing the same sort of thing. So I've defined L, and now L is a goal that I'm trying to prove. This is a thing to do. And I see there's a for all quantifier, so I want to strip that out, open up that quantifier, and now I can see the new proof state has that quantifier stripped off, and it's in the context. And then I want to do, in order to prove this, I need to do induction over that variable. Okay, so that does induction over the variable. And now this is the first case where n is equal to 0 in the induction, and that can be automatically discharged by Z3. Likewise, the next case, the successor case, can also be automatically discharged by Z3. And then finally, we can say that it says there's nothing on the goal stack left to do, so we can actually assemble the actual Knuckledragger proof object at this point through QED, and now we have a Knuckledragger proof object. Okay, so that's what interactive theorem proving looks like in Knuckledragger. So what is the core idea? If there's anything you take away from this talk, I kind of want this to be the thing you take away. The core idea is that how to chain together Z3 calls in a compositional way with as minimal layer as possible over top, as little opinion sort of placed on top of what the automated theorem prover is providing. And so what it is a core inference rule, the big inference rule of prove. And since there's one kind of mondo inference rule with many axiom schemas around this, this is a Hilbert-style proof system. That's sort of what those look like. It's implemented as an LCF-style kernel with a proof data type that is distinguished from other formulas. And you can get the formula out of the proof data type to manipulate it and do metaprogramming and tactical metaprogramming. But the only way to construct the proof data type is a small number of trusted constructors in the kernel, one of which is this proof function. And proof objects, again, are basically trees of recorded Z3 calls. That is basically what proof objects are. So here, using the kernel facilities, we can say that, like, by fiat, x is some constant that's greater than 0. So I never stop you from using axioms, and the ability to assert axioms is important for any interactive theorem prover. So I can assert that axiom, and then I can prove, given that axiom, that x is greater than -1, okay? And then I have a proof. And you can inspect this thing, and there's actually there's a theorem field, as I showed before, for the actual formula, and there's a reason field showing the sub-proofs that actually went into the proof call. But that's not quite the whole story. As I've used this thing, I've found that the quantifier instantiation of Z3 is really just not reliable enough to not have like a backstop, something that I can be guaranteed to work. And this is important for building the backwards proof system, as I'm about to describe. So there are actually quantifier axiom schema, basically to introduce and eliminate quantifiers. There's induction axiom schema that you actually need because Z3 doesn't have that internally. Here's one example. There's a Herbrand schema where if you have a for all quantified formula you want to prove, it's sufficient to prove it over the thing instantiated with the fresh variables, is basically what this schema says. So here supplies a proof object for any quantified formula of this form. And you could also instantiate proven formulas without going through Z3 itself. This by fiat just does it at the Python layer, saying that yes, this is a valid proof to instantiate a proven quantified formula. And likewise, there are the actual axiom schema that are hidden behind that induct tactic described earlier. Okay, so how does this backwards big lemma object work? It is not a core part of the system. It is something that calls kernel functions under the hood for you. And what it is, it's a mutable lemma object with a list of goals and recorded intermediate lemmas that are going to be useful. And what each tactic function does is it pops a goal, it records proof objects into the lemmas list, anything that might be useful to dignify the step you're trying to take right there, and then pushes new goals onto the proof goal stack. And then finally, L.QED assembles all the lemmas. It puts them into that by keyword field of a proof call of the top level goal. So that's how that works. And finally, a smorgasbord of different things that are just facilities inside of Knuckledragger. I'm kind of proud of these things. They're kind of fun. And I think these things are actually useful and important if you want to take the basic ideas over into an actual usable system. So first off, there's a standard library in Knuckledragger about reals and bools and sequences and nats and ints and lists and so on and so forth. This is growing all the time, and it's important to have these things. There's also, I've been playing with shallow embeddings of different kinds of logics, which I think is kind of fun and interesting. Intuitionistic and temporal logic and some others. There's also a facility for quick check. Python has a hypothesis library for quick checking. And this is useful for getting quick, sanity checking of goals sometimes, but also to relate implementations to axiomatizations. So here, if you're trying to prove that n plus 0 is equal to n plus 1, obviously not true, well, the thing will find a counterexample, even adding 0 to 0, adding z plus 1 is false. That's not true. A search facility is very important for an interactive theorem prover. You need to find the appropriate lemmas that are in the libraries or previously. So there is a search functionality that scans through memory and will find anything that matches patterns, or there's a couple different forms of queries you can make. There's also a rewriting facility that operates over the Z3 AST, and this gives you controlled rewriting. Z3 supports simplification on its own, but if you want your own custom axioms or lemmas that you've used, or you want to only there isn't a lot of control over the built-in Z3 simplify functions. This can do that for you. So here's a simple example of using that. So there's a bunch of syntactic utilities that are useful for me implementing these various features, but I also think are interesting as an end user for doing automated theorem proving, implementing these sorts of things and implementing your own stuff. So there's just a bunch of little helper things. There's some locally nameless combinators for dealing with binders, unification and pattern matching stuff. So there's a unify function that returns the substitution of unification. There's some pattern matching facilities, and there's term orderings also, which was important for implementing, for example, Knuth-Bendix completion. There's a Knuth-Bendix completion solver. Here is completing the simple theory of groups and getting a completed rewrite system for it. Also, there is printing to external solvers like eProver and Vampire. They have different strengths and weaknesses compared to Z3. Basically, it prints SMTlib and TPTP output out of the Z3 AST and subprocess calls them. There's eProver and Vampire. There's reflection facilities to reflect an applicative subset of Python back into Z3. So here, for example, I can define a fairly natural-looking recursive factorial function, and by reflecting it, I can get it as a Z3 definition. I can use these nice if-then-else Python if-then-else. You can also evaluate back into Python layer Z3 expressions, or in the context of different Python modules. So other interesting subsystems are operator overloading. There's a sort of a minimal type class system and generics. There's SymPy interrupt, which is very interesting and very difficult to do that in an assured way. There's Axiom Schema related to ARB, which is a rigorous arbitrary precision library. There's inductive relations. There's also a small prolog facility. Some future work that I'm interested in pursuing is textual proof certificates and standalone checkers. Basically, I could print out a SMTlib file of a chain of things that need to be checked by a solver, and a standalone checker that could be written in Z3, C++ or C or whatever. Fill out more theories, of course. Filling out software foundations. I have the first couple chapters done. Extraction to C, Rustling, and Verilog. There's some facilities for that. eGraph rewriting. Some applications I've been tinkering on are binary verification of Ghidra P code through the Pi code library, Verilog importing via Yosis, the SMTlib output of Yosis. And if you've got other interesting ideas of where you think the system might be useful, come chat with me. So that's Knuckledragger, low barrier interactive theorem prover based around Z3. Here's a link, www.kdrag.com, to the docs. So there's documentation for all the different functions and things in it, and also a variety of blog posts and other documentation. Thank you for listening.